It is an absolute pleasure to welcome Professor Pulkit Agrawal to give our second IAIFI Colloquium. He's an assistant professor in the Department of Electrical Engineering and Computer Science at MIT. He's a part of MIT's Computer Science and Artificial Intelligence Lab. And of course, he is a senior investigator at IAIFI. Professor Agrawal's overarching research interest is to build machines that can automatically and continuously learn about their environment in the hope that the machine might develop what we would call common sense. This research direction encompasses computer vision, robotics, and reinforcement learning, which is precisely the thing he will tell us about today in this colloquium entitled Challenges in Real-World Reinforcement Learning. Professor Agrawal will answer questions at the end, which you may submit via the chats on YouTube or Zoom, or which you may ask at the end in real time over Zoom. Professor Agrawal, please take it away. Thanks.
Thanks a lot for the introduction, Jim, and thanks a lot for inviting me to talk in this seminar series. And I'm very excited about the IAIFI effort. So I was thinking about, I am coming from a background which is mostly computer science, and I don't know a lot about physics beyond my college courses. Right? But there is a lot of overlapping interests between what is happening in AI and what is happening in physics. So what I thought was I would start off this seminar by just walking through some examples of when to use reinforcement learning. So it's a question which comes up, should I use supervised learning? Should we use reinforcement learning? Should we use something else? So what I'm going to do is to start off with some such examples and to motivate when RL might be a good tool to use, and then talk about what challenges happen when we actually try to use that tool. Okay. So probably one of the most famous use cases or the regular use cases of a simplified version of reinforcement learning is when you visit a website and the question the website owner has is, which web page should he show you, or which product should he show you? So if you have 3 products, A1, A2, and A3, suppose a person comes in and he gets a product A2, he may or may not buy it, and that gives me some rewards, right? For an action, I get some reward. Similarly, a second person might come in and I might show her a different product, and she is also going to invest, maybe pay some money to my website. And as the store owner, my goal is to maximize my profit. So what is happening is there is profit per click on the y-axis, and there's data or time in the x-axis. And what I would want to do is to learn over time to maximize my profit. So I might have an algorithm 1, which eventually ends up figuring out what is the best product to show to which user. But I could also have an algorithm 2, which finds the same solution eventually, but it does it much faster. For there is a significant difference between the performance of algorithm 1 and algorithm 2, because it translates into how much money I have made. So this is one of those use cases where we need to make online decisions. I cannot wait to collect the data set first and then start making decisions. Right? So supervised learning, I would need to do that. But in many real world setups, that is just not possible. A second example is when we have to deal with very large state spaces. So probably a lot of you are familiar with the result of how deep reinforcement learning was employed to solve the game of Go. The problem is, in the game of Go, the state space is huge. Right? Some people estimate that it's more than the number of atoms in the universe. So in such state spaces, we can only explore a very small part of it. Yet, what we want to find are good insights. Right? What I mean is, by insights, we want to find good strategies to operate in these environments. Or in this particular scenario, we want to have a good strategy to play a game. Right? So what you can think of is reinforcement learning can help us explore state spaces which are huge and synthesize some knowledge. Now, to give one more concrete example, I'm going to talk about work from Kathy Wu, who is also a colleague at at MIT. Right? So suppose you have the problem of urban planning, and we have some simulators which can simulate how traffic might move. So although we have these simulators, but to simulate all possible traffic conditions is just impossible. Right? And therefore, to find out how I might solve the problem of traffic, if that is my goal, by using the simulator is also not very clear. So there was this, famous demonstration of the traffic jam problem, which was done some time back. I believe this was in Japan, where what they showed was even if you let the cars move in a circle, at some point you will naturally see this jam-like behaviors. So traffic jams, form automatically because of the way people are driving cars. So one question, you might ask is, how do I solve this traffic jam problem? And maybe my strategy is I want to introduce one automated car, right, which is this red car, and it's going to observe this blue car, right? And it's going to move depending on its observations. And the hypothesis is that maybe there's a strategy of moving which might break traffic jams or not allow them to happen. So right now, AV off means that the automatic car is not working. It's just operating as any other car. But at some point, we switch on the automatic driving mode on this car, and you see it's following a different strategy. It's maybe not sticking as closely to the other car, and that leads to this behavior where there are no longer any traffic jams. Right? So this is one more example where there's this complex simulator. I want to get some knowledge out of it, but it's very hard to get it. And reinforcement learning can allow me to get this knowledge. Right? So similar examples happens in robotic manipulation. Over here we have a hand. This hand has 24 degrees of freedom, right? And it's a continuous action space. So again, the search space is big. Yet I want to find a strategy to manipulate this cube. Okay. The other instance where reinforcement learning really becomes useful is, suppose I have an existing data set. So I have some starting location, and I have some data of how to go to some goals. Right? But if you look at these solutions, what we might find is that I can actually optimize the green path. Right? I don't need to go to the green. I can now actually follow the orange path. So reinforcement learning can be thought of as finding the shortest path. I can take data which exists and try to find connections between them or shortcuts between them, which allow me to reach my goal faster. So in summary, if I have online decision-making problems, if I have very big search spaces, either in form of simulations or some other way of expressing it, we can synthesize knowledge. A subset of that is controlling nonlinear systems. Another use case is improving existing solutions when I have a lot of data available. But if I just do supervised learning, I will maybe, for example, just for the orange and the green one, but by doing reinforcement learning, I can find these shortcuts between them. Right? So now let's look at what happens what are the problems which come in as I'm trying to use reinforcement learning for some of these problems. So I'm going to begin with this setup where I have a robotic agent. It's looking at a table which has a few objects on it. Its observation is just the image of the table. And we want to figure out actions which will lead to the agent rearranging these objects on a table. Similarly, I can ask the question, given the image of a rope, what actions I need to take to go and tie it as a knot? So the reinforcement learning approach says that given an action X or given the state X, I'm going to find a policy pi which produces some action A. Right? The policy is just a mapping from my state to my actions. When I take this action, I'm going to get to the next state, xt plus 1. And if this state is close to the goal state, we are going to get a reward. And the whole game is, how can we maximize the sum of rewards? So natural question is, how do I initialize this policy? So initially, because I have no prior information about the system, I can say I'm going to initialize the parameters theta to be random. But if parameters theta are random, what that means is that I'm going to be doing a random sequence of actions. Now imagine if I'm doing a random sequence of actions on this rope, what's the likelihood that I'm going to go and tie a knot? It's very unlikely that I'm going to do this just by random chance. This is exactly why reinforcement learning actually works in video games, because you can take a lot of data and you are just waiting that by doing many interactions, once in a while, I'm going to hit the reward. So you're pretty much just doing random search and hoping for the best. And once you get rewards, you try to incentivize those strategies. The other thing which is worth noting is that in these simulation environments, or when we are dealing with games, the reward is very well defined. It is the game score. But natural question is, what about in the real world? Now, if I have this image of a rope, and then I have this other image which shows a knot, how do I know what is the reward? I cannot measure the reward directly. This reward must be estimated somehow. So one strategy you might say, or we might come up with, is let me take the difference in images. But we know that difference in images is not a very good way to know if these two states are similar. Right? For example, if I just shift the rope, the difference in the image space is going to be huge. Right? So that isn't going to work. Alternatively, what one could do is to build a visual classifier which classifies, is this state the goal state or not? But how do we build classifiers? We go and label data. We rely on a human farm to label data for us, because that's the way we know how to build classifiers. But what happens if I change the goal to be something different? Now I need to repeat this process again. And if I change the goal, I need to repeat this again. Right? So in summary, the issues that we end up having when we are using reinforcement learning is that first, we require lots of data. It is actually unclear, where do rewards come from? And even when you are able to define a reward, those rewards end up being very task specific, requiring significant amount of work to define rewards and estimate rewards or measure rewards for a new task. So what I'm going to do is to kind of walk through these questions one by one and see how we can address them. So let's look at the first question, which is, where do rewards come from? So to make this, to drive home this point even more clearly, right? Let's imagine that the way you say the rewards come up is a human designer designing the rewards. For example, I have this agent, which is a simulated, humanoid, and we want to move right. And I give that reward and I optimize this agent. Now let's see what I end up getting. This agent does move on the right, but not in the way we expect it to move on the right, right? It goes on the ground and then it pushes itself to the right. Now consider another problem where I want this robotic agent to stack this red block on top of this blue block. So one very intuitive reward function is to say, well, first I want to raise this block and then I want to keep it. So maybe there should be some incentive for me to raise the block from the table. Right? Now what you would expect is the hand would go pick up the block and then raise it. But let's see what ends up happening actually. This agent again finds, a strategy which we would not intuitively expect it to find, but it does optimize the reward function. So what these are examples of reward hacking, where even though I define a reward for which if I find a solution will look like the solution I want, there exists many other solutions which can suboptimally optimize that reward. Right? And in many cases, there might also be many optimal solutions which give the same reward. And this is exactly what makes reward design actually be very tricky. For example, if I want this quadruped to walk over this simulated gap world, I get this policy which may not work. Then I'm going to observe the failure modes, modify the reward function, get a new policy. And if I don't like it, I might go and modify the reward function again. So essentially how research or even how implementing reinforcement learning algorithms practically might look like this. It is more of grad student reward descent. Right? I have a problem, I define a reward, I look at what the system is doing, use my intuition, modify the reward. We keep on doing it for a bit. At some point, you do end up getting, an agent which can walk, but, it's not, the best way or the desirable way of doing it, because in some ways you can say, well, this learns from the reward only, but there was a lot of manual effort which went in to design the reward function. So similarly, let's look at some of the latest and greatest benchmarks in reinforcement learning. So I'm taking one example, which is the meta world. Over here, there are these different manipulation tasks that need to be performed, like pressing the handle, pressing the button, reaching, closing the window, opening the window. Right? And now let's look at, some of the reward functions that are designed. So over here, there's a hand which I want to go and pull this object out. Right? So this is what we want the system to do. Right? Now let's look at the reward function. For the reward function, first for reaching, right? It says the reward is negative of the distance. If you are within 0.04 of the distance, use this, but otherwise use a different reward. So once you come close to your goal, now you need to go and close the fingers. Then, we have a different way of picking, right? And there are all these funny numbers, like 0.04, 0.005. And after you pick up the object, you have another program with more funny numbers, right? Exponential to the power with C2, 0.01. So this is almost, there is a program which was written to specify the reward function. So it turns out if you go and look at the benchmarks in reinforcement learning, all these benchmarks have reward functions which are designed by someone, and that did not happen overnight. It actually took them a significant amount of time to design the reward. So the pessimistic view is you might say, well, are we designing algorithms which work with rewards, or are we designing rewards which fit to algorithms? Right? It's an interesting question to ask, especially as you are trying to apply reinforcement learning to new problems. So this, is a big challenge and also an active area of research of how do we tell the system what to do, and then how do we optimize for that. So for example, one way you can think of overcoming the reward specification is actually to demonstrate what the system should do. For example, over here, I want to insert this tool into a particular object, and this person is demonstrating the system how to perform this task. And then over time, the system can make use of these demonstrations and train further and then learn to do the task. So, so one thing we can do as well, I can use demonstrations to specify what we want the system to do. So it can potentially solve the problem of where do rewards come from. And the demonstration also has an additional benefit that I don't need to explore as much. Now, what do I mean by that? What do I mean is that initially, if you see, the system is kind of coming close to the to where it needs to insert because of the demonstrations, and now it just needs to fine tune near this point to figure out how to insert, right? So the exploration problem becomes much easier because of the demonstrations that were provided, and therefore you can get significant gains in data efficiency. But one problem is that these demonstrations are actually very tedious to collect, right? I mean, this person really has to move the robot, and doing it for different tasks just becomes an hairy effort. The other thing is, it looks maybe somewhat easy if you have never moved a robot before, but if you actually try to move a robot or even do this through virtual reality, it is quite painful. But this is a practical thing which you could do if you can do. Right? So now let's consider, this problem of block stacking. It's a simple problem where I have these, objects on the table and I want them to go in some particular configuration. And my state space over here is position and orientation of the blocks. And my action space is what is the position of my end effector, which is the fingers of my robot, and whether the gripper is open or closed. Right? Now, if we use standard RL on this task, it ends up failing. Why does it end up failing? Because the rewards that I defined were sparse. Now, what do I mean by a sparse reward? Right? So suppose I have my current location. I'm going to illustrate what I mean by sparse reward through this, this toy example, which I hope will convey why you would want sparse reward and what is a sparse reward. Suppose I have this agent at the current location and I want it to move to go to a goal location. Now, what I'm going to say is the reward is +1 only if you are close to the to your goal. Now, the good thing about sparse rewards is that they're easier to define, right? Because now I'm not, so if you look at the other examples I was showing, you have to write the whole program. And if you're writing this whole program, there are more chances that you would find unexpected behaviors than if you can directly say, this is the reward, right? +1 if you succeed, 0 if you fail. But for example, if I'm stacking 2 blocks, if I say reward is +1, if I stack them, 0 otherwise, then you will only stack. Then you wouldn't learn the strategy of flipping the cube, which only happens because you're trying to make the rewards be more dense by giving it distance of first raise the block from the table and then keep it. But once you start modifying the reward function in those ways, you find more unexpected solutions. Right? So the takeaway is that sparse rewards are typically easy to define, but they come with their own set of problems. The problem is if I have a sparse reward, if I take some actions, I'm going to get no reward, right? Most sequence of actions are going to end up with no reward. Right? And this is what creates the exploration problem. So one thing, which has been used in, like reinforcement learning quite a bit is how can we combine demonstrations and reinforcement learning? And, we can use these to, perform these tasks, for example, like stacking these blocks on the table. But as we know, giving these demonstrations could be very tedious. So are there, alternate ways that we could explore which do not require me to give demonstrations? So one idea is that we could use a curriculum of tasks. Could say, let me start with an initial state. I will give you an easier goal to begin with, and then I'm going to make this goal slowly be more complex. Right? So this task curriculum is easier to specify than the demonstration because it is at the task level. Right? So it's not as tedious, could be done more easily for a greater set of applications. Right? So for example, going back to our setup of arranging these blocks, there is a natural curriculum I could provide in which I just simply increase the number of blocks from 1 to 2 to maybe 5 or 6. So let's look at what happens when I give a task curriculum. So on the y-axis, I am showing the number of blocks which are stacked, On the x-axis, I'm showing the amount of time for which training happened. So the red line is, or the purple line or the red line is showing when there was no curriculum, versus the orange line is showing an example when there was a curriculum. So what you see is that even though when I give this curriculum of going from 1 to 5, my algorithm only ends up stacking a single block. So you might ask, if I have stacked one block, why was I not able to stack 2 blocks? Right? So why did this curriculum fail? Right? So one intuition behind why the curriculum may not always work is, I have a state space which only has one block over here. And from this state space, I'm learning a policy. Now, if the solution I found is going to be useful for stacking 2 blocks, then when I take this policy to this expanded state space, it should still work, right? To at least do something. But if the policy does not generalize to this new state space, then I'm not going to transfer the solution which I learned initially to my second subproblem. Right? So even though I have subproblems which are increasing in complexity, my neural network might overfit to solving subproblem 1 and might not generalize to subproblem 2. And therefore, it would null the benefits of any curriculum. Right? So then the question becomes is, well, curriculum learning is a good way to specify tasks of increasing complexity, but there's a caveat, right? The caveat is that we need to be careful in how do we represent those tasks, because otherwise my information from the initial tasks might not work for my future tasks. So, one way to overcome this is to come up with good architectures to represent my state space. Right? So one thing that we experimented with last year was using graph networks to learn a representation which can easily generalize from set of 1 to 2 or 2 to 3 and 3 to 4. So it turns out that if you choose a good way of representing the state, and then if you do a curriculum, then you can end up learning how to stack 6 blocks just using reinforcement learning. Now you can come back and ask the question, is it just because I had a good representation, or is it because I had the curriculum? Right? Turns out both are required. So if you see the green line, that is depicting when we use a better representation of the state, and also use the curriculum. If you don't use both of them, the performance is much worse. So we can go back and compare this with approaches which relied solely on human demonstrations. So this was some work out of OpenAI, which came back 3 years ago, and they had the success rate and the number of samples it takes to stack towers. Right? So even for this simple task, it's 2.3 billion examples. Right? Versus using this curriculum-based technique, we can both improve our performance, but also significantly reduce the amount of time it requires to achieve this task. Right? And then the other benefit you have of a good state representation is that we can generalize to new tasks that one might not have seen at the training time. Right? So for example, there could be, we could generalize to stacking blocks to towers which are much taller than were there in the training time, or even arrange these blocks in some more interesting configurations. So the takeaway is that in order to solve the problem of where do rewards come from, you can do demonstrations. There are some problems associated with it. You can try to resolve demonstrations by creating a curriculum of tasks, but there are caveats that you need to be careful in both how you define those tasks, and also do you have the inductive biases which will help your system generalize to a slightly more complex problem from a simpler one. Right? Now, the third thing, so now there are more things that we could be doing to overcome some of these problems. Right? The one thing we can do is we can say, while I am exploring in my environment, let me not wait to find the rewards before I learn anything. So let me make use of my interaction with the environment and learn something which is going to be useful when I get future tasks. Right? So I can learn some skills in anticipation of future tasks without really caring about the reward function. Right? This is about, let's figure out how does the world work if I don't have a reward function, and maybe what I learn about the world is going to be useful when I do get a reward function. So for instance, we have these robotic systems which are interacting with their environment. For example, on the top left, you see a robot just pushing objects. On the bottom right, you see a system playing around with a rope, and on the bottom left, you see an agent just moving around in an office environment. Right? So these agents start off with almost no knowledge about the world, and they're interacting with the world to learn something about the world. Right? Now the question is, what do I mean by this something? So one thing you can say is, well, I have my current observation. I'm going to interact with the world. I'm going to get my next observation, and we're going to build some models. And the reason we are building models is that now if someone gives me a task eventually, then I can leverage these models to solve that task very quickly. So one useful model to build is to predict what is going to happen in the future. Because we can always leverage such models to do planning. So if I have my current state xt and I have my action at, I can try to predict my future next state. And we're going to do this through a function f, which has parameters theta f. So while this problem seems intuitive, it raises a question. The question is, what is the space in which I'm making predictions? So one space which is the easiest to do is to say, let me predict, not easiest to do, but easiest to formulate, is to say, let me predict how the world is going to look in the future, pixel by pixel. Right? It is easy to formulate because I get the world, I can observe the world from my camera now, I can take an action, observe the world from my camera at the next time. So I have these two observations, which I can use to learn this, to minimize the distance between x hat and x. This is what is called as a forward model in the pixel space. And there has been a lot of work in building these forward models, which take images as input and try to predict what is going to happen in the future. But turns out, building these models is really, really hard. Because just imagine trying to predict how everything is going to look in the future in exact detail. Right? It's very hard. But if I have a hard problem, I should not give up on the problem, right? But I think the question we should ask is it just a hard problem, or is it really the right thing to be doing? To illustrate this point, consider that I have this glass bottle, and suppose I drop this glass bottle. This glass bottle breaks, and I get all these pieces of glasses and water. Right? So it's easier to predict the fact that the glass bottle broke, but it's very hard to predict the exact location of these glass pieces. But the thing is, I don't have supervision for things like that the glass bottle broke and that I should not step over this glass. So instead of predicting pixels, maybe we should figure out some good representations of the data in which I want to forecast the future. Because it's going to be much easier, and maybe I can also make much more longer term predictions if I find the right abstraction to forecast the future. For this leads to this question of, given the image, can I learn a feature space Z, which is not just trying to predict the pixels, but is, has some other properties which will help me make good predictions about the future. For the image space is attractive because I have access to that data. More abstract spaces, I don't have access to that data. So this is what essentially motivates the use of self-supervised learning. Right? Can I come up with other objectives which do not require human to provide me with the objective for learning Z? Right? So one thing that we have explored is to say, well, I can do another task. I can have this input Z and ZT plus 1 and try to predict my own action. And this can supervise the learning of Z. This is what you could call as an inverse model. Take my images as inputs and predict me the action. And this inverse model helps me learn useful features. So what we can now do is to learn a forward model in this feature space Z instead of the pixel space X. So we can train both these inverse models and forward models together. So this is pretty much what we can do in all of these setups, and see if the same set of algorithms or the same set of ideas can help these systems learn useful skills. So the way we're going to test it is to say, well, I have my current state, then I have my goal state, and now I want to come up with a sequence of actions which is able to push this current state to my goal state. Right? So what you see, for example, over here is the system pushing this object, and these are instances of objects which the system has not seen before. But okay, it's pushing, right? Maybe pushing is easy because I just need to figure out the relative direction, and then I can go and push it. But what about maybe going to the task of manipulating ropes, right? One example that we considered initially, I have the system in the current configuration, then I provide a goal, which is say tie a knot, and the question is, can my system actually go ahead and do it? So it turns out that after the self-supervised learning of inverse and forward models, the system can actually solve this task. The accuracy is, as a disclaimer, the accuracy is not 100%. It's about 60% on this task, but it's significantly higher than what you might expect from just random exploration. The same thing we can try in case of navigation. Right? So what we can do is we can take a system to a new environment in which I don't have access to a map. Maybe I also don't have access to 3D sensors. What I see is the current image, and I want to go to a goal. So if I have no information about the system and I want to navigate to the goal, what would I intuitively do? One thing I might do is to kind of turn around, look left, look right, and then try to go towards the goal. So this is, what our system ends up learning. It learns this policy of turning around, and then it goes to the goal. Now these things, like navigation tasks, you can also do with current algorithms such as SLAM. But over here, we did not have to specify the turning actions. Right? Turning is an emergent behavior which the system learns on its own. Right? So what these examples are demonstrating is that by interacting with data, we can develop algorithms which help us learn skills, which can perform tasks in new environments, or even tasks which the system might not have seen during its interaction with the environment. Right? So what we have seen is that by self-supervised learning, we can learn a model of how things work, which can be used to solve a wide range of tasks. Right? There is still data requirements which are needed because you still need to interact with the world, and it doesn't completely solve the problem of where do rewards come from. So the one thing which comes up is, because I am not having any rewards from the environment and the system is exploring on its own, it might not explore a lot. Right? So what we would want to do is to incentivize the system to explore more. Right? So can we learn the model that the system has right now to say what it should explore next? Right? So just to drive home the point, if I have the environment and I'm exploring by moving, then if I'm doing random exploration, I might only explore a very small part of the environment. So instead of just choosing any one of the random actions, what I would like to do is to choose actions which actually expand the horizon of what we have explored. So this is, one more set of directions that is super interesting and fascinating, is how can we make a system explore new and new parts of the state space. Right? So some work, which we did over here was, in context of this game of Mario. So I have this agent which I take as, I have this game of Mario and I'm observing the image, right? And if I press left, the agent goes left. If I do right, the agent goes right. If I do top, the agent goes up. If I do bottom, nothing happens. And as we talked before, we are learning this model which says, given the agent and the action, what is going to happen next, right? So over here, the prediction is go up and then go down. This is exactly what you find happening in reality. So everything is good. But sometimes, when you say, what is going to happen if I do the right action? If you have never seen this pillar before, you would think that you're going to move through the pillar and go to the right. But actually, this agent goes and it gets, it hits the pillar. So there's a difference between what happens in reality and what the model's prediction is. Right? Now, similarly, if I'm able to incentivize the model to follow its own prediction errors, it might end up going closer to this pillar. Right? And once in a while, when it is close to this pillar, it might take the action of jumping up. Now it might, jump up and it predicts it is going to fall down because that is what happens most of the times. But in this specific scenario, the agent never comes down, it gets stuck. Why? Because there was a pillar on top of which it could stand. So again, there's this gap between prediction and reality. So what we can do is we can make the agent be curious about these prediction errors, and then what this leads to is this agent learning the strategy of coming close to the pole and maybe jumping over it. So we can make it a bit concrete, right? I have my current state, I have a policy which I'm trying to learn, and this policy is for exploration. If I take my action A, I get to my next state, right? And I'm using this data to learn a model. And this model produces me a reward, which is my prediction error, which I then optimize using reinforcement learning. Right? Now, the same set of questions we can ask again, right? If I'm learning this forward model, in what feature space should I learn, right? One possibility is I could learn it in the pixel space, but we have seen that this is undesirable. So, what we want this agent is to become only curious about things that the agent can affect, or the same motivations that we had previously, right? We want to learn in some abstract feature space. So what we can do is you can use the same technique which we had, which was we learn a feature space which can predict the action, and then we build a forward model in the feature space phi. Right? And then we measure the reward, which is how different is the future in this feature space phi, which is a curiosity reward. Right? Now we can go and see how well this policy works. Right? For example, over here, this is showing an instance of this agent which is able to learn these. So if you see in this in this video, we are starting off with an image. The agent doesn't have access to any game rewards. What I'm showing you is a policy that the agent learns by only maximizing its own curiosity reward, right? And what you see is it learns these skills of jumping over these pillars, killing enemies, so on and so forth, right? So these skills kind of emerge automatically without, me requiring to, bake in any knowledge. And, these skills also end up being transferable, right? We can take it in one environment and then go to a different environment, and you will still end up exploring these state spaces. Now it turns out, you can do these things in different setups. You can also go to navigation, and you can learn how to navigate by just following, this curiosity-driven exploration. Now, in the interest of time, I'm going to skip, a few things which, I don't think are needed. So now what we can do is we can actually improve upon our self-supervised model learning by doing more exploration. But one problem, which ends up happening when we are doing this self-supervised model learning is illustrated by this particular, experiment. So what we were trying to do was, we had this, like this creature, like the mini cheetah, and we want to learn for it to move forward, right? And what I'm showing you is the return on the y-axis. On the x-axis, you're seeing different sizes of models that we have used. Right? Now, what we're going to do is, instead of having this very simple background, maybe make it more complex, right? By putting some, natural images or videos in the background, right? So what you now find is that with this distraction in the background, the model performs much worse, right? Which illustrates the problem that if there is sufficient complexity in your visual data, it's much harder to learn. And as you see, the model capacity actually increases. Sorry, the performance increases as we increase the model size, right? So what is happening is the model is spending most of its time, trying to model the background, which is irrelevant, right? So, how can we, overcome this problem, right? So one method which I talked about in the previous work was using inverse models. So they can, mitigate this issue to some extent. And turns out that we can also reformulate, MDPs in a particular way to overcome this problem, right? So for example, if I have my observation OT, I can take an encoder to get a state S plus, and I want to learn the state to predict the rewards, right? So right now, in the inverse model setups, we were not using any reward to learn a good feature space. But now what we're going to see is, can we leverage reward in interesting ways to not pay attention to information which is distracting, right? And I'm also going to learn another, state which cannot predict the reward. So the hope is that state S plus is going to capture information relevant to the reward, and S minus is going to capture information which has nothing about the reward. But I also want to be able to predict what is happening by combining both of these sources of information, right? And then I'm going to only use S plus to roll out my policy and then get rewards. So it turns out, if you do this optimization, what you end up finding is the states S plus correspond to only, caring about things that are relevant, and S minus ends up capturing things which are irrelevant. So we can go ahead and, compare this against different methods. So the raw observation is what you're seeing on the first row. Second row is showing you some prior work, and third is showing like the new MDP formulation which can help overcome this problem. And of course, you can do the usual set of things where you can measure performance on Atari games, and we are able to improve, or this algorithm can improve performance even in those setups. So what we looked at now is how we can learn task relevant models. But the thing that we also looked at was that exploration has some benefits, but exploration can also be undesirable at some times, right? So for example, if my robot is exploring, sometimes it can just go and fall down, right? And this is not good, right? Because the robot can damage itself while it is exploring its environment, right? So the point being that online data collection is not always practical. Like sometimes we just have a big data set and there are severe constraints on how much interaction we can do. And we must learn from this existing data set. And this is what is covered under offline RL. So just a brief intro of offline RL is as following. Suppose I have my state and I have my action, then I go to my next state. Right? So I have a data set of my state, action, state transitions. And I might have an existing data set. So typically, when I have existing data sets, we employ off-policy learning. A popular off-policy learning is Q-learning. So what I've written over here is just the typical Q-learning update. Now, the thing that we want to do is that suppose I optimize this Q-learning, then I'll end up getting a learned policy, right? And now I can use this policy and execute on a state, right? But this policy might say, predict this action A prime. Now, if I was collecting data online, I would have actually acted the A prime and, and verified if A prime actually leads to a higher reward or not. But in the offline setup, because exploration is expensive or costly or I cannot verify this. Whether A prime will actually lead to a good reward or it will not lead to a good reward. Right? It's something what the model is predicting. Right? So it is possible that we can overestimate the Q value. So it turns out there's some work from Berkeley which showed that if we can put additional constraint which minimizes the Q value while also updating the Q values through the Bellman operations. Right? So we are trying to be conservative in our estimates of the Q value. And this is called as conservative Q learning. So it turns out this helps us to learn from offline data sets. Right? So now we can look at offline learning in different setups. For example, I'm showing you some environments where there are these creatures moving around. And on the right-hand side, you see a data set which I might have of kitchen interactions. Now, how can we improve offline learning? There's one question which Anurag considered in his recent work. And what I'm showing over here is some data that I already have from different trajectories of this ant moving in this environment. And what we're going to do now is we're going to take these trajectories and cluster them. And these cluster corresponds to learning some kind of skills or action primitives. So mathematically, I can say that I'm going to produce a sequence of actions from the state and some latent cluster Z. And now when I have a reward, I'm going to only do optimization in the space of my Z's instead of doing it in the space of these low-level actions. Now, each Z might correspond to, say, 5 low-level actions or 7 low-level actions. This ends up being easier to optimize because we can reduce the plan length significantly. So, then there are regular numbers that you will find in any paper showing that, we can significantly, outperform things in, these setups. So the other aspect, which is really important for any real world system is to learn safely, whether it is online interaction or offline interaction. So I know I'm running short on time. So what I'm going to do is I'm going to just jump a few things and just talk about this one last thing, and then I'll stop for any questions, right? So in most of this talk, what you saw was, we have been using deep neural networks as our workhorse for reinforcement learning. But neural networks have many desirable and undesirable properties. So it makes sense to investigate, how these deep networks are working. Right? So one, common intuition you might have from classical machine learning theory is that a deeper a network is, the more number of parameters it is going to have. Right? And there are more parameters, classical theory says that we should learn more complex functions. It turns out that this is not the case, that actually the deeper the network becomes, you end up learning even simpler functions. Right? And we can go ahead and say something more about what we mean by simplicity. What we mean is that deeper networks find lower rank solutions. Right? So this is something which was known if you had a linear deep network, but this was something which was not known for deep nonlinear networks, right? So, what you find is that as the network becomes deeper and deeper, it finds more and more lower rank solutions. So what I'm showing you is a solution space of a network, a single layer and a 2-layer network. So what you find is a 2-layer network has solution space which is much lower rank. And you can also visually see it. So on the x-axis, on the y-axis is the rank, and the x-axis is the increase in depth. So as the depth of the network increases, the rank also reduces. So we feel, such investigations into what the network is doing is, critical for us to be able to tune our algorithms or to make better reinforcement learning algorithms that work in the real world. Right? And with that, I'm going to stop and take any questions that you might have.
Excellent. Everyone, wherever you are, let's thank Pulkit for his wonderful colloquium. Pulkit, that was a lot of fun. I'm sure there are many questions. So what I'm going to do is I invite you, if you have a question, to raise your hand or type it in the chat and I'll read it out. And if you raise your hand, I'll call on you and I'll let you unmute yourself.
No.
Maybe I'll start while questions I'm sure are coming in. So you were sort of, I liked what you were saying at the end. I forget exactly what you called it, but there was this opal, and you talked about how this latent space sort of a single Z might represent many actions. Some problems that I've run into in my work is a case where the action space just gets really, really big. And so I don't just have to worry about reward engineering, but I also have to sort of worry about action engineering, sort of how to compose the actions in a way that reduces the size of my action space so that I can learn effectively. Is Opal doing something like that? Or maybe more generally, might you have some comments on how to think about reducing action spaces efficiently?
Yes, so I think that's an excellent question. I think this also comes up, a lot if you're doing recommendation systems, right? If you have newspapers, articles that you're trying to recommend, right? You might have many, many, many different newspaper articles that you want to recommend, right?
Yes.
So there's, one expansion which happens in that dimension. So one way people are approaching it is by learning embedding of the action space, right? So for example, if you have different news articles, you can say, I want to learn an embedding of each news article, right? So for example, I could leverage GPT-3, for example, to create an embedding. So now, although my action space in the discrete sense is huge, right? And it's also variable, but in the embedding space, it is much smaller. And it is a constant size embedding vector.
Right? I see.
So that is some techniques, which one could use. In the Opal work, the embedding is over a temporal sequence and not over, the large possibilities of the action space.
I see. So it's not just doing dimensionality reduction in the action space of the type you just mentioned with an embedding vector, for instance. It's
doing it in time. It's doing it in time instead of in the other dimension.
I see. So in some sense, doing it in time, you could think of as composing a sequence of actions together in a useful way or something like that.
Yes. So you want to be able to do some kind of hierarchical reasoning, right? So you have a sequence of actions where you can just reason by just combining those actions together.
Yes, absolutely. Very good. All right, well, thank you for answering my question. Are there other questions out there? Don't be shy. Oh, I'm sorry. Here's one in the chat. I wasn't monitoring the chat. That's my fault. Do you try to learn a state space as you're trying to learn the policy, or do you do it independently at some prior time?
So in most of the work, we are learning it simultaneously. So if you look at, for example, the Mario work, it was simultaneous. And yeah, I mean, most of the works, it's happening simultaneously. You might pre-initialize it at some points. For example, sometimes you might take a pre-trained computer vision model, but then you almost always end up fine-tuning it with the task.
Excellent. That seems to have satisfied the questioner. Any other questions out there for Pulkit? So one question that I get, that I think you probably get also a lot as an RL expert is, and you mentioned it sort of a little bit at the beginning, but for some physicists that are out there that are wondering what sorts of problems should they apply reinforcement learning to, or when should they really not apply reinforcement learning and use some more basic optimization? Is there any sort of guidelines you can give people for when it might be a worthwhile thing to look into?
Yes, I think that's a great question. So I think one thing to think about is if there is a need to explore. I think that is when you need some form of active learning or reinforcement learning. If I already have a data set, but I don't need to explore, but I just need to optimize a particular criteria, right? Then I would probably just use supervised learning because I don't need to collect additional, data, or I don't need to improve. So yeah, so if I have a strong reason to believe that I do need to collect more data, I think, that is one place where reinforcement learning could be useful. The other is, if there is a system that I want to control, but I don't have a good model of it, right?
Yes.
So that is another place where reinforcement learning is useful. But then many times it could turn out that I have a system which I don't have a model for, but maybe the number of dimensions of the state space is not that huge, right? So maybe in that case, I can just sweep the state space and do system identification, by learning. So that could just be supervised learning, right? For example, if my state space is 3-dimensional, I can sweep it, and then I can just do supervised learning to produce the actions, right? So in that case, I might not need reinforcement learning. You could use it, but it might be an overkill. Right? But the state space is much bigger that I cannot sweep over it, then reinforcement learning would be useful in those setups.
Absolutely. Let me ask a follow-up question. So oftentimes, whether in my work or my friends' work, we're exploring some mathematical system with an infinite but structured state space, or some physical system like gauge theory or string theory. There's often just a huge state space to explore. So in cases like that, like you're saying, if you want to do some sort of search, some sort of exploration in search of some goal, it's a natural thing to do, particularly because you can't observe all of the state space. Yeah. But one thing that I really don't have a good sense of is, classic optimization algorithms for exploration or for optimization, like genetic algorithms or simulated annealing. I mean, sometimes we find via experience that a genetic algorithm on some task may just not work as well as reinforcement learning, but I don't have a good sense of when or why that occurs. I mean, is there any sort of consensus in the field about that?
So I don't think there's any consensus in the field about that right now. What people have shown is that you can do, you can do much more basic versions of reinforcement learning, which are going to, work as well as the whole reinforcement learning frameworks, right? In some of the benchmarks that people have. So I think the thing to think about is that genetic algorithms and reinforce, they're both trying to approximate gradients, right? And they are approximating the gradients in a slightly different way. So genetic algorithms are encouraging much more diversity. So it's like shooting everywhere. Versus what reinforcement is doing is, you're starting somewhere and then you're trying to grow, more out of it.
Yes.
Right. So I think that's the, basic intuition. Now, depending on the problem setup, one could use one or the other, or one could also combine both of them, right? You could start with, the way to see this to genetic algorithms, and then let, RL kind of do the expansion. Then you might ask, even genetic algorithms do some expansion, right? Because they mutate and then you fine tune. So in what scenarios would reinforce, works better than genetic algorithms? I think that is unclear.
Yeah, but I take your point well, that for things where you need sort of large jumps in state space associated with gross exploration, genetic algorithms might do better, whereas RL can be sort of better for fine-tuning small steps in state space or something like that.
Yes, or maybe also a different perspective is, if you could create instances like self-play, right, where you can have the system play against each other. I think that is something it's unclear. So maybe I think there are two things to think about, right? One is, how do you set up the data collection? And then how do you optimize it? I think both things are interesting to consider. Because self-play is something that is just the way I set it up, right? And I could optimize self-play with both techniques, right? I could use genetic algorithms to optimize it, or I could use reinforce to optimize it.
Yes.
So, yes. I think maybe the question should be, I would say there are two questions. I think one question we should always ask is, are there more creative ways to collect data? Which I think has been the biggest success in computer vision with self-supervised learning, right? And then the other is, how do I optimize it?
Absolutely. But Pulkit, you and I can talk all day long. There's another question in the chat that I'd actually like to get to. So Nihar, would you like to, and there's another one coming in too, would you like to unmute yourself or should I ask your question for you? If I don't see a hand, I'll go ahead and ask it. So Nihar says, if I have an idea of how a physical model should act, can I incorporate this into my reinforcement learning model, or will this miss some global minimum/maximum? Are there any examples of this?
Yes, so I think this is well studied in model-based reinforcement learning, where you could start out with an approximate model of the system and then fine-tune it. For example, you might say, if I have a non-rigid system, maybe some part of the system, maybe if I have a non-rigid system, then a rigid system is a good approximation to it. But if I find the control through it, I may not be able to do well, right? So we can start off with a rigid system and then use RL to improve upon the solution, right? I mean, I actually had, a few slides on this, but, because of time, I skipped it. But, I don't think you can say anything about global minimum or maximum. What you can empirically demonstrate is if you simulate the entire complex system, it becomes so slow to simulate that you can't really do practical things with it. If you use a simple system and simulate it, you can find solutions, but the solutions are not accurate. So what you can do learning is to create a fast simulator, right, which works almost as well as the better simulator. And then you can leverage that for doing learning.
Excellent. There's a question from Constantine in the chat now. Constantine, would you like to ask it live? It's about domain knowledge and domain expertise of a particular variety.
I think you're muted, Constantine.
Is Constantine?
Yes, I unmuted myself, sorry.
Oh,
so parents are always fascinated looking at their little kids stacking cubes, right? So this is a similar activity here. And so I'm wondering, have you talked to any early child developmental psychologist to figure out what's the reward function for the baby, right? Is the baby stacking the cubes because it wants to make a tall tower, or is it because the baby eventually wants to knock it over and make a big noise or explosion? And so maybe the key is, the entropy of the system, changing the entropy.
Yeah, so I think this answer depends on, the psychologist or the child developmentalist you ask this question to. But I think one common theme is that babies are setting themselves goals and they're trying to go for goals, and these goals are just changing all the time, right? There's some approximations to what they might be doing. So some people say they're doing it out of their curiosity, right? Some people would say they are doing it because they're trying to learn a model of how the world works. Right? But I don't think or some people will say they'll do something until they get bored and then they will try something different. But I don't think there is a concrete mathematical notion of what kids are doing other than the fact that they're setting themselves goals and they seem to switch between different goals. So I think I think Josh Tannenbaum at MIT, I think he loves, blocks and stacking towers. And this Alison Gopnik at Berkeley, I think she loves the curiosity view of what kids are doing. So I think there are different perspectives which are out there.
I see. So the field is split. Interesting.
Yeah, the thing is, it's very hard to know. It's very hard to quantify what those goals are optimizing over. What they have come to the conclusion is that they're not just doing reflexes, right? They're just not doing sequences of actions, but that they're setting themselves some goals. But what those goals are, it is unknown.
I see. Thank you.
Maybe just to physicists that are out there that are thinking of potentially playing with reinforcement learning. One thing that my friends and I have found as physicists trying to do this is that you often have some state space and action space and reward structure in your head, but then you actually sit down to do it and you realize that it has a lot of tinkering. So you can get good results, but if you play around with any physics system you care about, you'll find yourself doing some sort of engineering rather quickly. That's one of the interesting things. Is there a final question out there for Pulkit?
Well, I mean, I'll just comment on that, Jim. I think that's what roboticists also do right now. They tinker with the reward function, as I was trying to communicate through some slides.
Yes. Yes, and there's a lot of tinkering involved for exactly this reason, that it's not clear how the net's going to optimize what sorts of strategies it will learn. But yeah, I hope that more physicists find some examples of places in the research where they can use these techniques, because it's rather different from supervised learning, obviously, but it has a sort of a very different sort of flavor and set of things that it can do. But yeah, so. Well, Pulkit, thank you for the wonderful colloquium. It was great to hear about your work. I think this is my first time hearing about your work at such length and this area that you're interested in. We really appreciate it. It was a great colloquium. It will be on YouTube later. And if you could send us your slides, that would be wonderful. So everyone that's out there, let's thank Pulkit one more time. And we will see you in 2 weeks for our next colloquium. Thank you very much.
Thanks a lot, Jim. And